Good day, class. For today's organic chemistry lesson, we'll be treating alcohols. In our previous lesson, we did the hydrocarbons, that is, aliphatic and aromatic hydrocarbons. And we said aliphatic hydrocarbons are alkanes, alkenes, and alkynes. We also looked at aromatic hydrocarbons to be benzene, and we looked at the monosubstituted benzene, which is methylbenzene. For today, we're going to begin with alcohols, like I earlier said. And we're going to see that alcohols which contain only one hydroxy group are called monohydric alcohols. For example, we have that as ethanol, and it is a monohydric alcohol. We also have propanol. That's propanol, and it is also a monohydric alcohol. That is, in essence, what we are saying here is all primary alcohols are monohydric alcohols. Alcohols which contain two hydroxy groups are called dihydric alcohols. Example of dihydric alcohols include ethane 1,2-diol, ethane 1,2-diol. This is the structure of ethane 1,2-diol. And you can see that it contains two hydroxy group. Ethane 1,2-diol is dihydric alcohol. Alcohols which contain three hydroxy groups are called trihydric alcohols. For example, glycerol, otherwise known as propan 1,2,3-triol. This is the structure of a glycerol: CH2OH, CH2OH, and CH2OH. This is propan 1,2,3-triol, otherwise known as glycerol. Okay. Non-aromatic alcohols have the general formula. We say non-aromatic alcohols have the general formula CnH2n plus 1OH. That's plus one hydroxy group. Aromatic alcohols are aryl substituents of aliphatic alcohols in which the hydroxy group is separated from the benzene ring by at least one methyl group. What we're saying here is this. This is the structure of aromatic alcohol. That is phenol. This is the structure of phenol. That is the aromatic alcohol, phenol. And we said that aromatic alcohols are aryl substituents of aliphatic. Said aromatic alcohols are aryl substituents of aliphatic alcohols in which the hydroxy group is separated from the benzene ring by at least one CH2 group. For example, phenylmethanol. This is a non-aromatic alcohol. And now, looking at aromatic alcohols, we have, for example, phenylmethanol. This is phenylmethanol. And the other is phenylethanol. This is phenylethanol. Alcohols are classified depending on the number of carbons joined to the carbon next to the hydroxy group. We say alcohols are classified depending on the number of carbon. Alcohols are classified depending on the number of carbons joined to the carbon next to the hydroxy group. For example, primary alcohols are those that only one carbon atom is joined to the carbon next to the hydroxy group. That is what we mean here is, in primary alcohols, in the structure of primary alcohols, the hydroxy group has just one carbon attached to the carbon on which the hydroxy group is attached to. For example, ethanol. You can see that ethanol has just one carbon atom attached to the carbon atom on which the hydroxy group is attached. This is what we mean here. We have a CH3. In this place, carbon is attached to this carbon, and this carbon is attached to the hydroxy group. An example of a secondary alcohol, we say that secondary alcohols are alcohols which have two carbon joined to the carbon next to the hydroxy group. Say there are two carbons joined to the carbon next to the hydroxy group. Secondary alcohols. Let's look at an example. We have this structure could otherwise be written as such. This is propan2-ol. Propan2-ol. The structure of propan2-ol could also be written as such: CH3 OH, CH3, H. That's the structure of propan-2-ol. And we're going to see that tertiary alcohols have 3 carbon joined to the carbon next to the hydroxyl group. So tertiary alcohols have 3 carbons joined to the carbon next to the hydroxyl group. Example of tertiary alcohol, let's look at it. I'm going to have CH3, CH3, C, that's carbon attached to the hydroxyl group. Another carbon attached to the hydroxyl group. We have CH3, CH3. This structure is otherwise written as CH3, OH, CH3. The name of this compound is 2-methyl this compound is 2-methyl propan-2-ol. 2-methyl propan-2-ol, or 2,2-dimethyl ethanol. 2-methyl, the name of this compound is 2-methyl, because the methyl group is attached on the second carbon. 2-methyl propan-2-ol. That is it for a tertiary alcohol. Next, we'll be looking at the physical properties of alcohols. The preparation of alcohols. Preparation or synthesis of alcohols. The first method by which alcohols can be prepared is by reduction of aldehydes, ketones, carboxylic acids, and esters. And the first method by which alcohols can be produced by reduction is by reduction of aldehydes and ketones. Remember that the reducing agent often used here in organic chemistry is lithium aluminum tetrahydride in dry ether and then water. Now you can see from the screen there aldehydes and ketones undergoing reduction. Aldehydes and ketones are reduced to alcohols using lithium aluminum tetrahydride in dry ether and then water to form primary and secondary alcohols respectively. In this reduction, we're going to see that aldehydes are being reduced to form primary alcohols, while ketones are being reduced to form secondary alcohols. As you can see there, we have propanol, which is an aldehyde, being reduced using lithium aluminum tetrahydride in dry ether, then water, to give us propanol, that's propan-1-ol, which is the primary alcohol indicated there. Now, the next reaction is propanone, which is a ketone, being reduced to give us propan-2-ol, which is a secondary alcohol. Aldehydes and ketones, in the presence of nickel as catalyst and hydrogen, are reduced to primary and secondary alcohols respectively. What we're saying here is aldehydes and ketones can also be reduced using nickel catalyst in the presence of hydrogen, where, for example, ethanol will be reduced. That's ethanol reacting with hydrogen will reduce the presence of nickel to give ethanol, primary alcohol. Propanol will also be reduced in the presence of nickel catalyst to give propan-2-ol. The next reduction we'll be looking at is carboxylic acids, that is reduction of carboxylic acids. Carboxylic acids are reduced to alcohols in the presence of lithium aluminum tetrahydride in dry ether and then water. You can see the reaction there is going to yield an alcohol. Example, we have ethanoic acid being reduced to give ethanol. And the next will be esters, that is reduction of esters. Esters are reduced to alcohols in the presence of water and in an acid medium. Esters are reduced to alcohols in the presence of water and in an acid medium, or aqueous sodium hydroxide. You can see there, esters being reduced to give alcohol and acid. Example, we have ethyl ethanoate being reduced in the presence of sodium hydroxide, that is aqueous sodium hydroxide in water, to give us ethanol and sodium ethanoate. And also, we also see that ethyl ethanoate can also be reduced in the presence of, in an acid medium, in the presence of water, and then reflux to give us ethanol and ethanoic acid. The next is hydration of alkenes. Hydration means addition of water. Hydration of alkenes using phosphoric or concentrated sulfuric acid as catalyst or potassium permanganate in an alkaline solution yields alcohols. We're going to see here that the first reaction there we have ethene reacting in the presence of, undergoing hydration in the presence of phosphoric acid and high temperature and pressure is going to yield us ethanol. Ethene again in the presence of concentrated sulfuric acid and water will yield us ethanol. But now we're going to see that when hydration is taking place in the presence of potassium permanganate, then a diol is produced. Like you can see here, we have ethene in the presence of potassium permanganate to yield ethane 1,2-diol. In the presence of hydrogen peroxide and osmium tetraoxide as catalyst, alkenes form diol. We say in the presence of hydrogen peroxide and osmium tetraoxide, like you can see there, hydrogen peroxide and osmium tetraoxide is going to yield us a diol as well. And the next we'll be looking at is going to be hydrolysis of halogenoalkanes. By heating with an aqueous alkali, that is by heating halogenoalkanes with an aqueous alkali such as sodium hydroxide or potassium hydroxide, alcohols are produced. As you can see there, we have bromoethane being hydrolyzed and reflux. It's going to give us ethanol plus bromide ion. Bromoethane in the presence of potassium hydroxide reflux is going to give us ethanol plus potassium bromide. The next we'll be looking at is by fermentation of sugars using zymase as catalyst. Fermentation of sugar takes place using zymase as catalyst. Now you see there, glucose. Then the formula of glucose is C6H12O6. In the presence of zymase, it's going to give us 2 molecules of ethanol and carbon dioxide gas given off. Next will be the physical properties of alcohols. The lower alcohols are colorless liquids. Alcohols have high melting and boiling points than alkanes of comparable relative molecular mass and other compounds with same relative molecular mass due to hydrogen bonding between alcohol molecules. What we're trying to say here is alcohols have higher boiling and melting points than alkanes and other compounds of comparable relative molecular mass. When we talk of comparable relative molecular mass, we take, for example, if you are comparing a certain alcohol, say ethanol. If you are comparing ethanol and ethane, ethanol and ethane, you see that ethanol has a higher melting and boiling point than ethane. This is so because of hydrogen bonding between alcohol molecules, which means that between alcohol molecules there is the existence of hydrogen bonding. For example, let's look at these three alcohols. We have butane, C4H10. We'll compare it with ethanol, C2H5OH, and also compare it with propanone, which is CH3OCH3. Here we're going to see that these three compounds have almost same relative molecular mass. For example, the relative molecular mass of butane is 58 and the relative molecular mass of ethanol is 46. That of the next compound there, propanone, is 46 as well. But the alcohol is a liquid at room temperature and pressure because of extensive hydrogen bonding, whereas the other two compounds are gases as a result of van der Waals forces. Branched chain isomers have lower melting and boiling points than those with unbranched chain isomers, which here will mean that the branched chain isomers have lower melting and boiling points due to lower surface area. Short chain alcohols are readily soluble in water because they can form hydrogen bonding with it. The short chain alcohols are readily soluble in water because they can form hydrogen bonding with it. That is, they can form hydrogen bonding with water. As the alkyl carbon length increases, the solubility in water decreases. The next thing we'll be looking at is the reactions of alcohols. Next we'll be looking at is the reactions of alcohols. And the first reaction we'll be looking at there is combustion. Combustion means burning in oxygen. The burn in oxygen, that is the burn completely in oxygen, that is in excess oxygen to form carbon dioxide and water. As you can see from the reaction there. And the next reaction is reaction with metals. They react with metals to form alkoxides with the liberation of hydrogen gas. As you can see there we have ethanol reacting with sodium to give us sodium ethoxide and hydrogen gas evolved. On adding water to the alkoxide regenerates the alcohol. For example, if this sodium ethoxide produced is being added with water, reacted with water is going to regenerate our initial ethanol plus sodium hydroxide. The next reaction is oxidation. Oxidation involves the hydrogen on the carbon joined to the hydroxide group. This involves the hydrogen on the carbon joined to the hydroxide group. The different classes of alcohols oxidize to give different products. Thus, this is used to distinguish between the different classes of alcohols. That is, primary alcohols, secondary and tertiary. The oxidizing agent is acidified potassium permanganate or potassium dichromate. You can see from the first reaction that primary alcohols are oxidized to aldehydes and then to carboxylic acid because they have two hydrogen atoms on the carbon joined to the hydroxide group. And you can see there ethanol being oxidized to ethanal, and ethanal is further oxidized to ethanoic acid. Then we see that the further oxidation of aldehydes to carboxylic acid takes place only in the presence of excess oxidizing agent. Primary alcohols are oxidized using aqueous potassium permanganate or potassium dichromate and in the presence of dilute acid. Secondary alcohols are oxidized only to ketones because they have only one hydrogen on the carbon joined to the hydroxide group. And secondary alcohols are oxidized using aqueous potassium permanganate or potassium dichromate in the presence of concentrated acid and heat under reflux. Which the difference here is primary alcohols are oxidized in the presence of same potassium permanganate or potassium dichromate and the presence of dilute acid. Meanwhile, secondary alcohols are oxidized to ketones in the presence of potassium permanganate or potassium dichromate and in the presence of concentrated acid and heat. Tertiary alcohols, on the other side, have no hydrogen atoms attached to the carbon linked to the hydroxide group, so it's not oxidized. So tertiary alcohols are not oxidized at all. The next reaction is dehydration. Alcohols undergo elimination reactions in which the elements of water are removed to form either an alkene or ether. Good dehydrating agents are aluminium oxide and concentrated sulfuric acid. Complete dehydration to alkenes. The first is complete dehydration to alkenes. When alcohol vapor is passed over heated aluminium oxide at high temperature, an alkene is formed. Like you can see there. And the next, when alcohol is also treated with excess concentrated sulfuric acid at 180 degrees Celsius, an alkene is formed. And partial dehydration to ethers, when excess alcohol is treated with concentrated sulfuric acid at 140 degrees Celsius, an ether is formed. As you can see from the reaction there, that's an ethyl ethanoate. And the next reaction is esterification reaction. Alcohols react reversibly with carboxylic acids to form esters and water. The reaction is catalyzed by concentrated sulfuric acid and in the presence of warm water. As you can see the reaction there of esterification, you see ethanol reacting with ethanoic acid, depending on conjugated sulfuric acid and warm to give us our esters, ethyl ethanoate, and water. The next reaction that you can see there is halogenation. That is the reaction with chlorinating agents. Alcohols react with halogenating agents such as phosphorus pentachloride and dichlorosulfur 4 oxide or methyl halide to form halogenoalkanes. With chlorinating agents, they react with sulfur pentachloride. With chlorinating agents, they react with dichlorosulfur 4 oxide in the presence of sunlight, in the presence of slight heat or warmth, to yield a halogenoalkane, and sulfur dioxide gas is given off. And white fumes of hydrochloric acid are also given off. They also react with phosphorus pentachloride without heat, that's in cold, to give us a halogenoalkane and phosphorus and phosphoric acid chloride plus white fumes of hydrochloric acid, that you can see from the reactions there. This is used to test for the presence of hydroxide group in alcohols, water, and carboxylic acid, as they produce steamy white fumes of hydrochloric gas. Steamy white fumes of hydrochloric gas which they react with chlorinating agents. As when they react with chlorinating agents, they give out hydrogen chloride gas. They react with methyl halides. By the action of concentrated sulfuric acid on the appropriate solution. Like you can see, they use us a halogenoalkane. Now we're going to look at the test for hydroxy group. The hydroxy group in alcohols, water, and carboxylic acid produce steamy white fumes of hydrogen chloride gas in the cold with pentachlorofluoride, or in the warm with dichlorosulfur 4 oxide. That is, if you're reacting either an alcohol, water, or carboxylic acids with phosphorus pentachloride, or with phosphorus pentachloride in cold, or in the warm with dichlorosulfur 4 oxide. These compounds produce, the hydroxides in them produce steamy white fumes of hydrochloric gas. Now, distinguishing between primary, secondary, and tertiary alcohols, the first we'll be looking at is the Lucas test. The reagent is concentrated hydrochloric acid and zinc chloride. The reaction takes place at room temperature. The alcohols under investigation is shaken with zinc chloride dissolved in concentrated hydrochloric acid. Tertiary alcohols give a cloudy solution immediately due to the formation of chloroalcohol. Secondary alcohols give a cloudy solution within 5 minutes due to the formation of chloroalcohol. Primary alcohols give no reaction at room temperature. Iodoform test is also used to distinguish between the various classes of alcohol. Alcohols containing the structural formula. as such, we say alcohols containing the structural formula where R equals H, or where R can either be hydrogen or alkyl or aryl group. When warmed with iodine and aqueous sodium hydroxide, produces a yellow precipitate of triiodomethane. That's the iodoform test. This test is also positive with aldehydes and ketones. In our next lesson, we're going to be looking at aromatic alcohols, which is phenol.